Thanks for coming to today's talk. It's called Designing a Cluster Manager and Proxy. I'm Kevin Xiao. I'm a backend engineer who has been working with the Redis field for about 4 years now. And I've been a regular attendee of Redis conference over that period of time. As the title suggests, this talk is going to be broken up into two halves. In the first half, I'm going to be talking about a cluster manager project that I worked on a couple years ago at Machine Zone. It's called Trask, and it was designed to handle a few million operations per second. I'm going to be discussing why we decided to go with a custom caching solution. I'll also go over its overall design, some issues that we ran into, and some optimizations we made and our overall results. For the second half, I'll be talking about a more recent project of mine. It's a Redis proxy that I called Redis Flare. Actually, my motivation to build this proxy came from my previous work on the cluster manager. I'll talk about some of the useful features that I wanted to prioritize, the overall design, and also talk about a couple of topics that I needed to consider when building a proxy. This included supporting clustering mode and also implementing various sharding operations or sharding options. So first, let's talk about Trask, the cluster manager. First, a little bit of information about Machine Zone. Machine Zone is a mobile gaming company. You may have heard of their more popular titles, which include Game of War, Mobile Strike, and Final Fantasy: A New Empire. The overall theme of these games is that they involve a large number of players interacting in a connected, persistent game world. Also, I'd like to take the time to mention that while Machine Zone was gracious enough to allow me to present today about this cluster manager project, I'm not currently an employee at Machine Zone, and I don't have any affiliation with them, so I do not represent Machine Zone in this talk. So with that said, let's talk about why we decided to build a custom clustering solution as opposed to using an existing one. Ultimately, we felt that we didn't have an existing solution that met our particular needs. So in Machine Zone, we use Redis primarily for caching data that's backed by a SQL database, which is it's a very common use case of Redis. However, we really cared about avoiding stale caches or incorrect cache data at any cost. In fact, it was preferable to be unavailable and to have a service outage than to return stale data. The reason for that is because, I guess in the game world, if we have any incorrect data, these game transactions end up propagating that out to the game economy. And once it kind of gets out there, there isn't really a good way to fix that. Sure, we can roll back the world state to some previous state that existed before the transaction happened, but that would definitely upset many users as their progress will get erased. At least in a service outage, we could just restart the service and things can sort of be fixed from there. But if we ruin the game economy, then there's not really much we can do about that. And to be clear, a service outage is already a really bad thing. So it's just that giving out incorrect data is even worse. At the same time, we did want to avoid sustained outages. And that's because we had some really expensive requests that took a lot of cache round trips. So if all of those cache round trips end up hitting the database, then the request latency will be very high. So we did have some qualities of data usage that gave us some room to design around, however, and that was that there was a very high ratio of read to write traffic. When I did some benchmarking with our data usage, I found that even if we could safely flush out or delete every key in multiple Redis instances at the same time, and the data would regenerate extremely quickly, in a couple of seconds actually. And while the data regenerated, there would be a very minimal impact on the overall database traffic and also on request latency. So this meant that if we were ever in a situation where we weren't sure if the cache was completely up to date, we could just delete the cache and have it regenerate from the database. And that meant that if we were to go to the CAP theorem, we didn't need a strictly CP system. We kind of wanted a system a little bit in between. So there were a few alternative solutions that we considered. One was that we could have kept with our existing architecture, it was built with master-slave pairs. In that setup, when a master failed, the slave would get promoted to a master, and then if the master recovers, it'll come back as a slave to that new master. There were a couple issues with this. The biggest one was that the sharding logic was being done by the clients, so that meant that if we wanted to resize the cluster, then we had to update all of the clients. And if we're doing this with live traffic running, that was pretty tricky because we had to do it in such a way where we weren't introducing inconsistent sharding. It certainly was possible, but it was just a huge hassle to do so. Another issue was that with master-slave pairs, if the master fails, then the slave gets promoted, but during that process, there's no more redundancy, and then we're just left with one node for that pair. So that meant that DevOps was under a time pressure to address that failure issue and deal with it before any more nodes fail. So life wasn't really great on their end. We did also consider open source Redis cluster. So at this time, Redis cluster has been out for a few months or so it was a pretty recent development. So one issue with that was that we didn't really see any large companies using Redis cluster at that time at scale. So we attended Redis conference that year, and there wasn't much field reports about Redis cluster, and what little we heard about it wasn't really the most positive, so that was pretty concerning. In addition, I did some benchmarking on my own, and I found that one problem with it, one area of concern, was that it had a very high background chatter. So basically, the cluster instances end up doing sort of pings or health checks, or basically gossiping with other instances. And I found that if you configured it to do those gossips pretty frequently, like every second or so, it actually used a pretty significant amount of network throughput, especially when you hit about 100 to 200 cluster instances. So that was pretty concerning since we were hitting a pretty high level of network utilization even without any traffic. And in addition, there was another issue that was kind of a deal breaker for us. The failover speed wasn't really the most fast. Even if we kept about like a 1 second of gossip time, it would still take about 20 to 30 seconds to fail over. And if we wanted to mitigate the high background chatter by increasing that gossip interval, it would lead to slower failover speeds. So another option that we looked at was the Redis Labs Enterprise cluster. Ultimately, we kind of decided not going with that path, mostly because of pricing. We decided at our scale, it wasn't the most economic to use the enterprise cluster. We actually decided to go with designing our own custom solution. And also, at that time, the enterprise cluster also had a similar issue with the slow failover speed. I've heard that during that time, they were working on improving it. So this might be old news. So this is our previous architecture. Over here on the left, we have our web servers. We have a number of PHP processes connect to a single Twem proxy instance. Twem proxy is an open source Redis and Memcache proxy that was released by Twitter, and it's a proxy that we used extensively at Machine Zone. This single proxy instance on each web server wasn't used for sharding. Actually, it was just used for connection pooling. The Redis requests from these web servers point to virtual IPs, which then point to Redis master-slave pairs, as we can see on the right. On each Redis machine, we have multiple Redis instances. So on each Redis machine, we have a pacemaker or heartbeat process that's responsible for monitoring the health of the master, and it promotes the slave when the master fails. So this setup, because we didn't actually have a central authority on what was actually the master, if we ever got a network split between the master and slaves, there would be a problem where we have split brain scenarios, which, as I mentioned earlier, is extremely bad. So we actually address this by running physical heartbeat cables between the master and slave machines. That obviously wasn't the most ideal solution. There was a number of issues with that. So this is our design after we rolled out the new cluster manager. On the left, we have the web servers. In the middle, we have a new proxy layer. And on the right, we have the Redis machines again. In addition, we have a Zookeeper cluster in the bottom left. So for the web servers, we still have that single Twin proxy instance running on them. And they still do connection pooling. But in addition, they now do load balancing. They load balance the request to all the proxy instances that's available in the proxy layer. So in the proxy layer, we have another set of Twin proxy instances, and those are the ones that actually do the sharding. In addition to the proxy instances there, each of the proxy machines also runs a cluster manager process. Over here, it's called Trask Monitor, and it also runs a Redis Sentinel process. So the Redis Sentinel processes are being used to do health checks and monitoring for the Redis machine instances, and the cluster manager is used to coordinate the failover and the system. And each of those processes, the cluster manager and the Redis Sentinels, they form a cluster amongst themselves. So ideally, for the proxy layer, you'd want at least 3 proxy machines. So you'd hit at least a minimum of 3 processes in each cluster. Now, we also changed how the Redis backends were set up as well. We completely did away with replication because we found, since we could quickly regenerate the data, that we didn't need it anymore. So instead, we had Redis machines being separated into either the active pool or the backup pool. In the active pool, they're actively being sharded to by the proxy instances in the middle. And for the backup pool, they're left as empty Redis instances so that if any of the machines fail in the active pool, any of the backup machines can be swapped in. And finally, we have the Zookeeper cluster. That is solely just for leader election to keep an elected cluster manager elected. Only the elected cluster manager will be responsible for performing the failover or updating the configurations of the sharding. So there's many possible failover processes failures that can happen. Any of the different components can fail, or you can have a network split between any kind of connection. But perhaps the most common failure situation is if a Redis backend machine in the active pool fails. So I'm going to share that with you. So how that would look would be that first, the Redis Sentinels need to detect that that Redis machine has failed, and it does so by forming a consensus that that machine has failed. And by consensus, that's going to be a majority of the Sentinel instances. When that happens, it publishes on their PubSub channel that this particular machine is objectively down, in which case the Trask, the cluster manager, will pick that up and decide to black out that shard. So it generates new Twin proxy configs to replace that failed shard with a port that's guaranteed to fail. So actually, we just use some random port. And then Trask will perform a rolling restart of all the proxy instances to update to that new configuration. After that, it will do another step of reconfiguration where it will update the Twin proxy configs again to replace that blacked out port with the new backup machine that we popped from the backup pool. And then it performs another rolling restart of the proxy instances in order to update the configuration. So this was kind of designed so that if at any point in this step, if something goes really wrong or so, for instance, the cluster manager dies, it keels over, something like that, if you restarted the cluster manager or a new one gets elected, it can pick up where the old one has left off and finish the failover process. And in the meantime, the system will still be fairly stable. there were some issues that we ran into. One was that Twin Proxy didn't support runtime configuration reloading. So that's sort of the reason why we had to do the rolling restarts for the proxy instances. Because in order to reconfigure Twin Proxy, we had to kill the process and then start it back up again. And if we wanted to do that and update all of our proxy instances, then if we had live traffic, then we'll have a spike where in our request latencies and also in database requests, which is not ideal. So if Twin Proxy had some kind of ability to reload its configs with a command, then we wouldn't need to do any kind of rolling restarts, and it would make that failover process much faster. Also, I had some issues with the blackout logic with Twin Proxy, specifically for the case where there's a sustained outage for a backend instance. So if you have a backend instance that is just timing out or so, then how Twin Proxy works is that it will, after a number of failures or timeouts, it will apply a blackout for a period of time. After that period of time expires, Twin Proxy will add that backend instance back to the pool, which sounds pretty reasonable, but the problem here is that what would happen is that Twin Proxy would black out with a number of failures. It'll add it back to the pool and then try again and black out again. And over a period of time, you would have a trickle of requests that would time out fully or hit the max timeout. And even though the vast majority of requests is being dropped by the blackout, even that small little stream of requests of timing out was noticeable into our request times. So it wasn't really the end of the world, but it would have been nicer if Twin Proxy would validate that the connection was good to that backend instance before adding it back to the pool. Also, there were a few proxy level features that would have been nice to have from the proxy that Twin Proxy didn't have. These aren't really necessary, but they would have enabled some more interesting cluster manager features that we wanted to work on. I guess the basic one was that there's some keys that, or Redis commands, it didn't support, like multi-get or multi-set. Not too big of a deal, but it also didn't have the ability to do durable deletes, which is basically retrying deletes or writes to make sure that they actually happen on a Redis instance. Also, dual writing would have been very helpful with data migrations. And also something that would have been useful, perhaps, would be some kind of automatic shutoff system. So suppose that we get in a situation where you have a network split between different proxy instances, but this proxy can still connect with some clients and some backends. In that situation, we really want that proxy to just shut off its own traffic because it's a pretty bad situation to be in, and we just want to avoid having inconsistency. So that's where an automatic shutoff system could come into play. So now I'm going to talk a bit about some of the optimizations we made when benchmarking Trask. First off, we quickly ran into the limit with a 1 gigabit network. So I would suggest at least doing a 10 gigabit network. Once that was resolved, the limiting factor tended to be the proxy CPU usage. And we found that in order to, so Twin Proxy is single-threaded like Redis. So we found the best performance when we pinned one process to a physical core. In fact, we saw an improvement when we completely disabled hyperthreading on that machine. In addition, we also found improvements when we pinned the network queues. And we also manually steered some of the network queues to particular proxy instances. So what this would look like is that for a server machine with 12 physical cores, we would have 8 proxy instances, one assigned to 8 cores, and then the 4 remaining cores would be assigned to network queues and also used for other processes like the cluster manager and the Sentinel instances. And finally, performance in the failure scenario is heavily impacted by what kind of timeouts we set on the client side and the proxy side. So ideally, we would set the timeouts to be the smallest they can be without giving any false positives. And that meant that if our data usage was very varied, such as we have a few keys that are megabytes in size. That means that we'll have to keep a fairly large timeout for them. So we found that we wanted to enact some kind of data usage policy where all keys would be within a rough round of range, like in the kilobyte size or so, as opposed to doing megabytes. So with this cluster design rolled out, here's the overall results. First, we managed to keep failover time within a matter of seconds. Each overall system could handle more than 3 million queries per second. We end up deploying a few of these to production environments. We addressed the issue I mentioned with the old architecture. So we haven't had a fire related with Redis caching since then, during my time at Machine Zone. So we accomplished our original goal. The system seems pretty robust, and we've done extensive failure testing on live, so we feel pretty confident in the system. So overall, I'd say it's been pretty successful. So that concludes the first half of the presentation. Now I'll be moving on to the second half. This part will be covering a more recent project of mine, one that I've been working on the past half year. It's a Redis proxy that I called Redis Flare. This project I worked on independently after I left Machine Zone, but it's heavily inspired by my work in designing Trask. I wanted to design a proxy that would have some of the features that I felt were missing from Twin Proxy. So when I started this project, I made a list of the features that I wanted from this proxy. First off, the biggest one was runtime configuration reloading, the ability to change the configuration without restarting. The second one was that I wanted a better blackout mechanism, something that didn't have any issues with persistently timing out backend. Also, Redis cluster has certainly become more mature over the years. So I wanted to support clustering mode, since for organizations with older clients, it would be tricky or impossible for them to use Redis cluster, and a proxy is kind of a natural way to make that transition. Also, for nice-to-have features, I wanted to expand support to more Redis commands, like multi-key commands. I also wanted to implement dual writing, which can help with data migrations, and then also durable deletes, which can make more guarantees that a cache is actually being cleared. And finally, because this is a caching infrastructure, I didn't want to sacrifice performance in this regard. So at a minimum, I wanted to keep performance comparable with Twin Proxy. Let's talk a little bit about language choice. So for a proxy, I feel like a systems language like C and C++ are natural choices. In fact, looking at various proxy implementations on GitHub, almost all of them, as far as I can tell, were written in C or C++. I did find a proxy called Codis, which I believe is written in Go. But according to one set of benchmarks that I found, Codis has a much larger max latency, about an order of magnitude higher, actually. And I think that's largely because Go is a garbage collected language. So I think that illustrates to me why I should probably stick with a language where there's manual memory management. So my initial prototyping was in C, but there was a big problem with that, and I had very little experience with C or any memory management in general. So that meant I was making beginner mistakes all the time. I was running to seg faults on every iteration, and my progress was extremely slow. So around this time, I've been hearing a lot about this newer language called Rust, and one of the bigger features that it promises is this ownership system that helps check for these memory issues on compilation time. So I ended up implementing the proxy in Rust, and I found that it's been a pretty good experience. I found the ownership system helped a lot with avoiding the segmentation faults, and also taught me a lot about memory management in general. I also appreciated its error handling system, which I found pretty helpful with dealing all the system calls for I/O. So if you're trying to implement a proxy, I'd say that Rust isn't really a bad language to implement it in. So here's a summary of the overall design. I had a dedicated admin port for administrating the runtime config swapping. This admin port also doubles as a port where you could query for proxy level metrics. For the blackout logic, I had the proxy attempt to validate the backend instance before adding it to the pool. So in that regard, it's pretty similar to Twin Proxy, just with a slight tweak. At the core of the proxy, I kept a single event loop that handles everything: the timers used for timeouts, the I/O resources, the admin ports, and everything else. I used Metal I/O for that. That's a Rust crate that provides some cross-platform event loop abstractions. The main reason for that is I didn't want to implement specific implementations for KQ and ePoll and stuff like that. And also, I end up adding support for both Redis clusters and standalone Redis instances. And I went with the approach where I abstracted a whole Redis cluster as just a single Redis instance, which kind of feels a bit clunky, but I couldn't think of a way to approach it. So let's go over a bit on how Redis cluster works and how we can support it with a proxy. It was introduced in version 3.0, which I believe was beginning of 2016 or so. The way it works is that the key space is pre-sharded to 16,384 slots. And these slots are then mapped to cluster instances. This allows for a smooth, controlled data migration, as you can migrate one slot at a time at your leisure. In addition, clients end up predicting where the key should be routed to. So that means that in normal requests, the request latency is faster than going through a proxy layer. There's a direct connection from the client to the Redis instance that is actually housing that key. So that's pretty nice. But that does mean, though, that old clients can't support clustering mode because they don't have that ability to predict which instance to go to. And that's why a proxy could be a helpful way to add clustering support to these older clients. So what does a proxy need to do to implement to make all that happen? So first, it needs to know the state of the cluster. This means that it needs to know what instances are in the cluster, and it needs to keep a cache of how slots map to each of those instances. In order to initialize this cluster instance, it needs to be able to send out a cluster slots request. And that, when it does that, the cluster instance will respond back with the slots mapping of the entire cluster. And keep in mind that at a particular Redis cluster version, that responsible format changed. So if you're looking to support all the Redis cluster versions, remember that there's 2 response formats for cluster slots specifically. In addition, the client or proxy needs to use CRC16 to do the hashing. That's the hashing algorithm used by Redis cluster. So there are times when that cache of the cluster state isn't going to be the most accurate. That's going to happen when there's some changes to the cluster or there's a slot being migrated to. In those cases, the cluster instance can respond back with a moved or asked response. So any proxy trying to support Redis cluster will need to deal with both of those responses. And basically what those responses do is that they tell the client which instance actually houses that key, and to ask that instance instead of the one that the client is trying to ask. And the difference between the two is that one of them is more temporary than the other. And one thing to remember is that Redis cluster does have hash tagging. So what this is that if you have a key that has opening and close braces, Redis cluster will use that subkey to do the hashing instead of the whole key. And this is a pretty nice feature because it gives the users some control over how the keys get sharded to. For instance, if you have a bunch of data that's associated with one user, you can decide to have all of them get sharded to the same instance by using hash tagging. So if you're implementing a client or proxy, you have to implement the hash tagging in a similar way as Redis cluster in order for it to be compatible. Otherwise, you're going to see a lot more cluster instance misses, and performance wouldn't be as good. Now let's go over a few sharding options, and that's basically how we route the Redis requests to Redis backends. So with the simplest option, we can just not care about sharding at all and not even hash the key. And we just pick a random instance and route that request to that random instance. And that works pretty fine for load balancing, but it doesn't work quite well if you care about inconsistency because you get multiple copies of that key distributed across the instances. Also, it might not fit that well if the whole key set doesn't fit in a particular instance. Now, if you do want to do sharding so that there is one backend instance that's responsible for a particular key, then perhaps the simplest way you can do that is to use modulo. And how this would look like would be you would use a hashing algorithm to hash the key or subkey with hashtags, and you'll get an integer, and then you just take that integer and modulo it by the total number of Redis instances, and that determines which backend instance it goes to. So this is pretty nice because it's really simple to implement, and it's pretty performant. But there is a downside, however, and that's if you ever decide to resize the cluster. So if you resize the total number of backend instances, then what you're going to see is that the majority of the keys, roughly about like n-1 over n or so, will migrate to a different instance when you resize. And if you do that when live traffic is happening, then you're going to see a spike in request latency and also in DB traffic, as all those keys have to be regenerated. So there's a couple things you can do to mitigate this. One is that you can kind of pre-populate the instances with the new distribution and then migrate it over. But there's some concerns with consistency there, and it can be a pain to do that. And the other one is that you can use a different sharding type, like consistent hashing. So for consistent hashing, I believe it was designed specifically for this particular case, where it will minimize the number of keys that will migrate when you resize the cluster. I'm not going to go over the full implementation details of it, but the overall impact of using consistent hashing is that if you resize the cluster by one more or one less, you get roughly 1 over n over the keys that migrate instead of n-1 over so. So that's about a factor of n, and here n is the total number of backend instances. So that helps a lot. It doesn't come for free, however. So modulo, once you get the hash, when you do the modulo, that's a constant time evaluation. But I believe for consistent hashing, that's a log n, so if you have a decent number of backend instances, I started seeing a performance hit by using consistent hashing. But it's really not the end of the world. And so if you don't really care about having the absolute max throughput on your proxy layer, consistent hashing is pretty good. It's a pretty good trade-off to reduce the number of keys that get that migrate when you resize the cluster. And then finally, for another option, we can take a page out of Redis cluster and do something pretty similar. And that's where we pre-shard the key range to different slots, and then assign a mapping of the slots to instances. And that deals with this key migration issue because when you resize the cluster, you can just move slots one by one as slowly as you want. So that really minimizes the overall impact when you resize. However, I have to say it's kind of a more complex system. So for instance, in order to determine the actual sharding of the cluster, you have to maintain this slots mapping, and you need to make sure that slots mapping is synchronized across all the proxy instances in the proxy layer. But besides though, it's a pretty good approach for a distributed caching system. Oh yes, also one thing I forgot to mention about the slots mapping is that it doesn't suffer the same kind of performance hit from consistent hashing, because you're just doing a lookup on some kind of map, so that's probably like a hash map or an array. So let's talk a little bit about multi-threading. First of all, what advantage does multi-threading give us? I guess it's a little obvious. Well, because throughput tends to be CPU strained on the proxy side, if our proxy is single-threaded, we have to run multiple proxy instances in order to take advantage of having multiple cores in a machine. So if our proxy was multi-threaded, then hopefully we can get the same amount of throughput by just running a single instance on that machine. So this is pretty nice because it reduces the number of total proxy instances that you have to deal with if you're trying to, implement some kind of clustering solution. And reducing this makes it a little simpler on the cluster management side. If you have a smaller number of instances to deal with, it could possibly lead to like a faster failover time maybe. But I feel like in a cluster situation, this may be a negligible factor. For one thing, if we're running like a whole like proxy cluster with multiple proxy machines, we already have to deal with multiple proxy instances, multi-threaded or no. And the logic for managing both is essentially the same. And also, multi-threading, I feel like, has a pretty heavy cost, which is that it makes the code base much more complicated. So it introduces like a whole class of error cases that you have to think about and consider. And I kind of feel for like a proxy or like a piece of infrastructure or so, perhaps the most important factor about it is that it's stable and reliable. And so if you have, maybe these concurrency issues that you might have to think about in the code base, you can be a little less sure that it's going to run stably in a production environment with a lot of traffic over many years. Maybe sometime down the line, after a couple of years of running fine, you encounter some kind of concurrency issue. And I think in that case, it'll be really tricky to identify that. So with that being said, I feel that multi-threading is, while it would be nice, I would consider it more of a luxury feature. It's not absolutely necessary, but it might be something nice it's something that would be nice to have. So I guess for the Redis Flare proxy, I have a branch where I've added multi-threading features. I haven't really done much benchmarking or testing with it, so it's just going to remain in that branch for now. But perhaps in the future, I'll look into it more deeply. I'm just going to go over a list of random little tidbits or insights I got from implementing this proxy. The first one's a little bit obvious, I guess. It's that computation is going to be dominated by 3 categories: parsing, sharding, and I/O. So if you're looking to try to increase performance, I'd probably look at focus on one of those categories. One note about Rust in particular is that the default hash map implementation is not the most performant. And in fact, if I switched over to HashBrown, which is a different hash map implementation. It's a Rust port of a Google's Swiss table hash map, I believe it's called. And it is way faster than, for map operations than the default hash map implementation. Actually, I think they're going to be moving that over to the default in the future, so maybe you don't need to worry about this. But in the meantime, definitely use HashBrowns instead of the regular hash map implementation. Another thing is that for a proxy, it's very important that a proxy never gets in a situation where it misaligns the responses and requests. If you drop a request and you miss it, then all the subsequent responses that are being lined up are going to be mismatched with the corresponding requests. And that means all your answers or all your responses are going to be wrong, and it won't really get fixed until maybe the end of that pipeline or so. So that's really bad. So what this means is that it's, I guess, extra important to make sure that you handle all the failure paths associated with proxying. And I feel like with dealing with I/O in general, there's just a lot of system calls and like a lot of possible branching of error cases and paths. And here I found Rust's error handling to be a bit helpful with identifying all the possible scenarios there. And then for the last one, Redis keys and strings, they're binary. So I made this mistake where I thought they were only valid UTF-8, which is not the case. You can do like some pretty, I guess, interesting things where like you can put in like I think like a 512 megabyte image as like a Redis key or so if you really want to. So just keep that in mind. So what's next? I'm planning on working on a new open source project. So this is a open source cluster manager that will be using Redis Flare proxy, and it'll be designed to take advantages of some of these proxy features that I implemented that I talked about earlier. I currently have a multi-threading branch for this proxy, but there's some improvements I'd like to make, so that's something I would probably want to look into more. In addition, I also want to add some more support for more Redis commands. So currently it supports mget and mset and stuff like that. But I think I can probably expand that list a little bit. It's not really a huge priority, however. But what would be a little bit more interesting or useful would be adding more scripts and tooling with this proxy. So the idea behind this would be that it would make it much easier to do some basic like maintenance operations or doing stuff like data migrations or so. From my experience, they've been very painful, I guess, to do manually. And then also something that I would be looking into is getting some like images ready to go for the cloud to make it a little easier to get something set up with the proxy. Now, if you want to find out more information, Machine Zone actually has a patent related to Trask. It's called Systems and Methods for Managing a Cluster of Servers. I wrote a lot of the documentation there, so I've listed out a lot of the different failure scenarios that I didn't mention in this talk. So definitely check that out if you're interested. Also, for the proxy, you can find it available on GitHub at my account kex103 Redis Flare proxy. And also, if you have any further questions, feel free to email me at redis@kex.dev. And that concludes my presentation. Thank you very much.
Can we?
And now there's questions.
Yeah, so if you have a question, please raise your hand and I will hand out the microphone to you.
Can you share more details about what metrics you are exposing? Is it Prometheus metrics, or what kind of metrics are you exporting from your?
Oh, are you talking about the proxy level metrics? So that's something kind of similar. So Twin Proxy also has statistics and stuff like that, and that's going to be like bytes received, bytes sent, number of requests, number of errors, and stuff like that. So these are just like basic proxy level metrics that I want to expose. So that's what I was referring to. I implemented something similar for Redis Flare.
Any other questions?
Hello, and thank you for the talk. In the first slide, you correctly identified problems with the first version of Redis cluster.
Mm-hmm.
I just wanted to clarify why it was like that and how it was fixed. Basically, the problem was that each node pretended to do health check directly with the other node without trusting the JADIS
Right.
of the other. And this, actually, the Redis cluster failover, it was extremely fast even at the start, but because of this bug, also the instances had issues in order to agree going from the p-fail to the fail condition.
Mm-hmm.
So now how it changed. Basically now the number of messages is no longer quadratic but is logarithmic. And now the cluster nodes trust the view of the other nodes about a given node. So they have a lot less messages. This in turn makes the ability to go from p-fail to fail very fast. So if you configure, for example, a timeout of 5 seconds, after 5 seconds, like 100 milliseconds, they agree, and the failover immediately starts. However, this was exactly one bug in the moment you tested the Redis cluster. In general, Redis cluster improved in a significant way, especially in Redis version 5. And also, thanks for open sourcing this project, because we are also working at a cluster project, but in general, it's great to have choices. And as you can see, the client landscape is not evolving fast enough. So the proxies are a middle ground solution that could work. Thank you.
Mm-hmm. Thank you. Yeah, I guess on that comment is that if we were to kind of approach this project today, we would probably go with Redis cluster. And in fact, before I left Machine Zone, that was kind of the direction that we were heading to. And yeah, I'm also really excited about the new Redis cluster proxy. Thank you. Any other questions?
Any performance numbers you can share?
So I don't really want to. I'm not sure if I can speak about it since I no longer work at Machine Zone, so some of it is proprietary information. Oh, the proxy? Oh, so basically I benchmarked that on my own personal machine, and for it, the performance is very comparable. A lot of the variance is mostly noise, so I haven't yet benchmarked it on like a larger scale with, like separate machines, so that's kind of the next step.
Maybe a last question. Okay, thank you.
All right, thank you very much.